Hello, welcome back to 15-Minute Math. So we are finding derivatives of functions and we're using the definition of derivative to do it. Last video we focused on polynomial functions. In this video we're going to focus on non-polynomial functions. So I left the definition of derivative up there at the top so you can see it. Hopefully it's something you're familiar with by now. This limit is the important expression that we're going to focus on. And I just want to remind you that that is in fact just slope. It is just the change in y over the change in x. That's all it is. But we're trying to find the slope at a particular point instead of the slope, like a secant line, as you do normally with our normal slope formula. So it's just important that you kind of get it through your head that when we find derivatives of functions, we are finding the slope. We're finding the slope of the function. We're just finding the slope at a particular point versus the average rate of change, over 2 points. And so let's take a look at this function here. We have a nice radical function, square root function here. We're going to find the derivative of it. Remember, f prime is one way to denote a derivative. There are others, but I think f prime, using the prime notation is probably the most common. So let's do it. So f prime of x is going to be given by this limit. Delta x goes to 0. And also recall in your own class you might be using h there instead of delta x. I like the delta x notation. A lot of people like the h notation. It's just preference, preference in notation. So don't let that throw you off if you can. So let's see here. If I use this formula, I have f of x plus delta x. So I'm going to plug in x plus delta x for x. Okay, so it's going to look like that. Minus the original function all over delta x. Now, when we were working with polynomials, we did so I think it was a quadratic we worked with in the last example. We had to square out the quadratic and or the x plus delta x part of it anyway. Had some distributing to do, and then some terms canceled, and then when everything canceled, we were able to factor out a common factor, and then our delta x's just kind of went away. They canceled out, and if you do enough of those problems with polynomials, that familiar thing happens over and over and over. You kind of get used to it, but you can see with these radical functions, you don't get that same sort of behavior. This is going to have a different flow to it because I don't get any sort of cancellations like I did for polynomials. So what we're going to have to do is rely on an algebraic trick that we learned a little bit earlier on in this playlist, and that's when I am dealing with radical functions, oftentimes the way to simplify these limits is to do what we call rationalizing the numerator. And you might have some horror flashbacks of doing that. But remember, in order to rationalize the numerator, we essentially just multiply the top and the bottom by the conjugate of whichever part of our fraction had a radical in it. In this case, it's the numerator. And so when we multiply by the conjugate, really what we're doing is we're setting up a difference of squares. We have, let's see here, a minus b, a plus b, and you never can see this too many times. So recall that if I have an expression, a squared minus b squared, that can always be factored into a plus b, a minus b, and so we're essentially just running this backwards. Instead of taking the expression and factoring it, we have a factored expression, and we're going to put it back into this form here. So essentially all I'm going to do is I'm going to end up with a squared minus b squared. And so let's see here. We'll have the limit as delta x goes to 0. A squared will just kind of rid us of the square root up here. So we'll just have x plus delta x minus 4. And then a b squared is just going to, again, rid us of the square root, so we'll just have x minus 4. And if you don't believe that that is how that expression would get multiplied out, you can go ahead and FOIL it yourself, but that could take a while, so you may just trust me or trust the difference of squares formula rather than actually do the multiplication yourself. Now, on the denominator, I'm not going to multiply this out. And you'll see why in just a couple steps. So moving on down, trying to move on down. There we go. We'll move on down. Uh-oh, I'm running out of space. I think we can get it in with the limited space we have. So let's see here. If I distribute across this quantity, maybe I should just do it right up here. Then I'm going to have minus x plus 4. Okay, and so it's going to look like this, and you can kind of see this x will cancel this x. This minus 4 cancels this plus 4. It looks like to me delta x is the only term left in the numerator, which is nice and convenient because you can see we can cancel that with our delta x factor in the denominator. So let me finish writing this out, and we're going to go ahead and do that. So there we go. Boom, cancel, cancel. So really, this just becomes the limit as delta x goes to 0 of 1 over the square root of x plus delta x minus 4 plus the square root of x minus 4. And we can plug in now. We can just plug in 0 for delta x right there. And so I'm going to kind of come over here and do it right there. And so when I evaluate this limit, I get 1 over, it's going to be x minus 4, because if I plug in 0 for delta x, just get x minus 4, plus the square root of x minus 4. So again, all I've done is I plugged in 0 to try to evaluate my limit, which basically makes this term goes away. So we get x minus 4 on the left-hand side, and this x minus 4 is just getting copied straight over. But notice that, I've got 2 copies of the square root of x minus 4, so I might as well just write that as 2 times the square root of x minus 4. And so we've learned that the derivative of the square root of x minus 4 is just 1 over 2 times the square root of x minus 4. And there's our derivative. Okay. Now for the next one, we're going to evaluate the limit, but we're going to do a little bit more. So we're going to find the equation of the line tangent to this given function at x equals 1. And so maybe we should visualize what we're really trying to do here. So if I go to Desmos, you can see I've got this function graphed. I don't know why I've got x equals 3 on there. And there's what our function kind of looks like. We're going to be interested in the function at x equals 1. And so I want to draw the equation of the tangent line right at x equals 1. So let me kind of sketch in what I'm trying to find here. So there's our 1 point of tangency. So we'll have a line kind of like this. I'm trying to come up with the equation of that line there. Now, a useful fact that you may or may not remember from your algebra days is that the equation of a line can be written like this. Y minus y naught equals m x minus x naught, where y naught, x naught are points on the line. Or I'm sorry, it's the xy coordinate for a point on the line. And then m is the slope of the line. So if I can find the slope of this line, then all I really need to do is then plug in the points where that line would intersect our curve, which is obviously at x equals 1. And then I'm going to be golden. So our strategy is first find the slope at that point, which is exactly what the derivative tells us. This whole derivative business, remember, is finding the slope of the curve at a given point. Or more precisely, it's finding the slope of the line tangent to the curve at that point, which is exactly what we have drawn in here. So that m is going to be found by that process that we've already been doing. And then y naught, x naught shouldn't be too hard to find because we already know the point that we want this thing to be tangent at. So not a complicated procedure, with the caveat that we know that point slope form of a line. So let me try to get back to my whiteboard. Let's see here. There we go. All right. So here's the function I want to find. So the first thing I want to do is I want to find h prime. Let's see. There we go. Maybe I'll do this in blue again. Here we go. H prime of x. Well, let's do our formula. So it's going to be x plus delta x over 2 times x plus delta x minus 1. So there's my h of x plus delta x. Now I have to subtract off the original function. And this is all over delta x. Now, you might remember from a couple videos previous, might have been several videos previous at this point, that there is a way to handle these complex fractions, and the way that you do it is you usually just multiply through by the LCM of the denominators of like the smaller fractions that make up the complex fraction. So let's multiply the top and the bottom by the LCM of these, which I believe is just going to be 2x plus delta x minus 1. Maybe I'll put that in a square bracket. And then 2x minus 1, which I know seems complicated and nasty. It is kind of complicated and nasty, but it will simplify. It'll all kind of work out in the end. You just got to trust the process for a bit. All right. So what I'm going to do is distribute that numerator. And when I distribute here, notice that this will cancel this, and I'm just going to be left with 2x minus 1. So I'm going to get x plus delta x. And I guess I'll put the part in green that's coming from the right side, 2x minus 1. And then I'm going to have minus. Now when I distribute here, this side's going to cancel, and then but I still have that factor left, so it's going to be x. And then again, in green, I'm going to put the part that's coming from the right. There we go. So that takes care of our numerator. And then, like we've done in the past, I'm not really going to bother to multiply out the denominator. I'm just going to kind of write it as is, and I'm going to color code it like I've been doing. So let's see here. Oh wait, square bracket, then square bracket again. That's how I see it on the right, so that's how I'm going to copy it down. And so now again, it looks a little nasty maybe, but let's just kind of multiply some things out and let's see where that gets us. So on the left hand side, we'll have to do a bit of foiling. It's going to be 2x squared minus x plus 2x delta x minus delta x. So all I did was distribute, first, outside, inside, last. I don't know where all these arrows are going. I'm missing one. You can fill it in. You guys are all smart people. And then let's distribute here. So negative x. Well, first of all, notice that if I multiply this 2 out, that's going to be 2x plus 2 delta x. And so now when I distribute, I'm going to get minus 2x squared. I'm going to get plus 2x delta x, because I'll have a minus and a minus. And then I'm going to have to also distribute the x over here, so it's going to be plus x, and that's all over, that denominator that we've had. I'm going to drop the color coding just for the sake of not having to switch back and forth all the time. I've noticed a really disturbing omission. H prime is not given by this expression. This is given by the limit as delta x goes to 0. So that should be like stuck in between the equal sign and my expression here, and it should also be going here. And then we also should go ahead and tag this on here. So this is going to be the limit as delta x goes to 0. Kind of a small notational thing, but it changes the meaning of the expression enormously, so it is important. And as we've seen before, we're going to have some cancellations, so I'll do those in red. That cancels with that, it looks like. Minus x cancels positive x. And then so we're pretty much, I think, done with our cancellations. But what you should notice is, same thing as what we've had in the past. Everything that does not have a delta x, everything that did not cancel has a delta x in it, so I can factor that out. I have a common factor now. I know I'm running low on time. I know I'm 15-minute math, but I think this might end up being 16-minute math. Hopefully the YouTube police do not remove my YouTube name. All right, so if I factor out delta x, I'm going to have 2x. Well, really, I have 2x and 2x. So really, let's just go ahead and write that as 4x. So that's going to be 4x minus 1 over delta x. Oh my gosh, I forgot my limit again. I think having this time crunch is not good for my mathematics. That's okay. We will amend this in a second. There we go. So this is the limit as delta x goes to 0. That should be there. Anyway, we will cancel our delta x. And now we can just plug in. There's nothing stopping us from plugging in delta x being 0 now. So let's just go ahead and do that. So we're going to evaluate our limit. And we get 4x minus 1 over, it looks like 2 times, well, x, right? Because delta x went to 0. We just went ahead and plugged it in. So it's going to be 2x minus 1 times 2x minus 1. And most people would just write that as 4x minus 1 over 2x minus 1 squared. Whew. So that's our derivative. So that's h prime. And we are actually curious about the point where x is equal to 1. And so now we just need to find what is h prime of 1. Well, if I plug in 1, I'm going to get 4 minus 1 over 2 minus 1 squared, which is 3 over 2. So my slope is 3/2. Now let's maybe stop and remember that we're trying to satisfy this point slope form. We're trying to find the equation of the line tangent, and the particular form of the line is what that's the form we'd like, the point slope form. So when we know m now, and actually we know x naught because we know that x naught is supposed to be 1. So we have x naught, we have m, we've got 2 of the 3 things we need to know. We just need to know what's the y coordinate at that point of tangency. Well, if it's a point of tangency, then the y coordinate is going to correspond, the y coordinate of the line is going to correspond to the y coordinate of the original function. And so let's just go ahead and find the y coordinate of the original function, which remember that was x over 2x minus 1, so it's going to be 1 over 2 times 1 minus 1, which is, what is that, 1/2? No, it's just 1 over 1. That's just 1. So there's y naught. And so if I want to come up with the equation of the line, now I got all the information I need. It's going to be y minus 1 equals 3/2 x minus 1. So there we go. We've satisfied what the question was asking. We wrote the equation of the line tangent to the given curve at the given point, and that's what we were after.